So, good evening. Tonight I'm going to make a video which may be a other very important video for certain viewers, and other viewers, they might be bored out of their mind trying to watch this video. And what we want to touch on today is basically an issue which involves mortar mostly. And I picked two examples, and I hope the other channels are not upset about this, that I'm picking their projects or what they're working on. But they have two topics or two situations which fit into this topic, what we want to talk about tonight. And we need to delve a little bit into chemistry to understand this better, and a tad bit of history, but otherwise I will go through this. So we're basically going to have three segments of this. One is the green mold I had mentioned in the other video, has now appeared in that lady in Portugal's building, on one of the buildings she has in the basement. And the other one is a chateau in France. A fellow is rebuilding, he purchased it, and he put a vlog out, and there is some issues with clay, not with clay, but with mortar. And the loss of the roof due to fire and structural things, because that castle was built in 1886. And it is built differently than all the older castles. But again, this applies to any structure out of that time frame or area, or the building materials used in these buildings. Again, that doesn't make any difference if you have a barn in Portugal, Bulgaria, Poland, or in Germany, an old barn, if it is not a wooden barn, or in Italy, or anywhere in Europe pretty much, or if you have a house which is built with brick and stone, or if you have a castle, a chateau, a palais, or even a fortress, for that matter. Whatever you have, anything and anything in between is basically built by the same principles. Usually more manpower needed and more material needed. And I got to think about this today on how I'm going to make this video, because it touches on so many different topics. So let me say sort of a disclaimer. As we say, there's many ways to skin a cat, and so there's different solution to the issues we are looking at today, which can be solved differently. I'm going off by my experience out of this whole area, primarily what has to do with castles, and as that translates into other buildings, because a castle is never just a castle, because you have support buildings in these structures or in that setup, from bathhouses over staples to barns to repair shops, regular workshops and stuff like this, and administrative buildings and all sorts of stuff is involved on larger castle operations. So there's a wide variety of there, and like I said, is all of the supplies. The picture you saw with the acid rain, with the brick on one side and the dying trees, and the headline of the video, which is acid rain, that is the last part, which is the third segment of this video I'm going to touch on. We're going to have pictures, and I don't think I have any video, but I have pictures to explain stuff. But at the very beginning right now is, before we look at the three issues at hand and how this is all interrelated between mold development or fungi wood development to structural issues, and anything that has to do with mortar, since the mortar is basically what keeps everything together, and how the acid rain comes in, we need to actually get into chemistry. And I'm going to start here. I'm going to show you something. I have a little box here. Hope you can read this. This is a professional or semi-professional pH tester. Just in the case you have never seen anything like this. And this is the unit with calibration liquids. I'm going to show you this here. I probably should hold it up this way you can see it better. And this is a system which is really advisable to get if you have a larger. So you can see this here. There's a cup underneath here. The sensors on the bottom, the glass bubble here, basically. And we have a measuring cup which is filled to the fill mark. And that is one of the devices you will need if you have a larger operation. So we have a liquid here, which will give you the calibration numbers. Let me see here. On a temperature related to, let me see, does that zoom in? I didn't take a picture of it. Hey, where's my camera? Let me see if we can zoom it. No, we cannot zoom it. This is pH 4, and this one here, the green one, so it is acidic, and this is neutral, pH 7. And you basically have to set this unit up, calibrate this after, wash it and clean it after each use. And then it is ready to determine the pH level. And what we do with this, let me just say one more thing, is for those people or folks who are watching this who don't have a large building to contend with a, say, like add-ons which were done in a later time, and newer things and older things, and this is all mixed up, you probably can get a kit, a pool kit, not the one with the little paper testers for pH, but with the liquids, you know, where you can pour them in and you can test the pH out that way. They have these little test bottles with, I think, 1 or 2 liquids, and that will then show you the pH level. It changes the color, and then you put your color chart next to it, and then you can determine the pH level of what you're testing. And the first thing probably what you want to do is, whenever you have a brick assembly or stone assembly where the mortar is falling out now, like in this picture here is an example, you can see that the mortar has probably rescinded, I would say, by about a ½ an inch or so, probably good a centimeter, 3/4 of a centimeter, 0.7 centimeters to 1 centimeter, somewhere around there, ½ an inch. And what you want to do here is to scrape some of this up on the outside and fill it into a little cup, and then get distilled water, which is really important. You want to put some distilled water in there, not very much, and then you have to basically grind this down to the lowest level the sand in that mortar is going to permit. We want to dissolve any remaining lime which is in there to see on how the caustic content, what the caustic content is, leftover content is in that. And then you want to take a drill, and that is a very special drill. When you go to a dedicated or larger hardware store, they have a drill in various diameters, and the inside, the center of the drill is hollow. That allows you to take a drill sample out of a material going in. So what I usually do is I drill into the mortar, usually between bricks, you know, where you have the biggest area, and you go in probably with the 6 or 8 millimeter drill. And it has about a 3 millimeter, 4 millimeters so hole size. You can't really drill a big hole. This has to be fairly soft material. And then when I think that I'm about halfway into the wall or brick assembly, whatever it may be, I take a piece of tape and I mark it on the drill where this basically flush with the wall, where the wall ends basically. I put it on there, put it around the drill. This way I know exactly on how deep I went in there. And then I take a white piece of paper I disconnect the drill. You have to be careful when you pull the drill out. You have to kind of tilt it back so all of the collected samples are inside the drill. And then you just carefully take the drill out and put this whole stuff that comes out in a line on a white piece of paper. Now you can see roughly in what segments it is, and what it is like, and what it looks like. And then you take, say, like the first centimeter. So if you start from left to right, you're going to get the most inner stuff first. And then as more as it goes to the right, as more it is on the outside of where you started to drill. And you take that 1 centimeter, and that is the one you want to dissolve, because that is the core, basically, of your mortar inside a wall or whatever. It could be on a regular brick. The old bricks, they were probably, I would say, 15 centimeters, 20 centimeters long in that range, which is roughly about a foot, a little bit less than a foot. You want to get about halfway in there, and this will give you an idea. And the reason for this is this. Lime was harvested in lime quarries, it still is today. And then the quarry owner had usually a kiln set up, K-I-L-N, which is a huge oven where they put that lime in there. And then it was heated up to 900 degrees. It was basically transformed. I don't want to go on all the chemical formulas, because just to give you a simple idea. And depending on where the quarry actually is located in Europe or anywhere else in the world where you have a lime quarry, the quality varies. And the quality of lime is expressed in the pH level of the lime, the burnt lime, the actual lime which comes out of after the burning process. So when you grind this down very fine and then dissolve it in water, you will get a pH level somewhere between 10 to 10.9. As higher the caustic is, or the not the acidity, well, it's more caustic. It is caustic used here in the sense for a base, because lime is a base. Will do two things. It prevents the mold buildup, because that high concentration or that high pH level means it is fairly caustic. It is also not good for your hands, skin, or anything to get this on, because if any type of moisture with sweating or something like this can leave burns or irritations. So lime is something to be dealt with very carefully, with breathing mask and everything else. And so that is basically it. And that varied from region to region, from quarry to quarry. A lot of times, 100, 200, 300 years ago, some quarry owners, they did not heat their kiln up to 900 degrees Celsius. That will result in a lower quality lime to begin with, say like with a caustic pH level of say like 9, maybe 8, 9. So you're starting out with already an inferior material. Then comes the sand on top of it. And the sand, usually, if you go to a reputable dealer, to a building supply house where they sell building materials, first of all, the sand is dry and it is free of impurities. So if you store your delivered sand like the gal did in Portugal, which you're seeing right now, that is sort of a no-no. I hope you're not upset, Maya, that I used your picture here, but this was such a perfect example. I just had to smile when I saw this. When you leave sand like this exposed, you're going to have moisture go in there for one, and you're going to have impurities going in there. And these impurities will make your mortar, when you mix this, of lesser quality. You wind up with a lesser quality product, and it will not adhere as good, as it won't last as long. So when you get sand, especially this type of fine-grained sand delivered, is you want to store this at least a foot above the floor to begin with, and then cover this with a tarp so the tarp cannot fly off. And you want to put it in the shade. You don't want to have that exposed to the sun. And you want to lift the tarp only up when you need some sand out of it. You take just the amount of sand you need for your mixing what you have intended to use at that point, and then you cover everything up. If you have sand which gets wet because it was stored like this, the easiest way to deal with it is to take a shovel and put it out on a large wood board, for instance, in the sun, and then make like a 1-inch layer, 2 centimeters or so. Let it dry, completely dry. You can work it through by hand. When you feel like it in the sun, if it is completely dry, you have to run this through a screen and to filter any impurity out. So the filter, the screen has to be just a tad bit larger than the largest grain of sand you have in there. I mean, since you bought it, you know what the size is. So you have to size this, and you want to get this then into a bucket, into a container to keep it from getting contaminated again. The same as with storing the actual lime. When you purchase lime, you want to keep that dry and dark. That is really the main reason for this. So the caustic aspect in lime does two things. It functions as the glue, so to speak, and it actually cleans the entire area, so the sand and this whole thing can stick better to it, and it keeps any type of fungus away from being not able to grow because the substance is just too caustic. So and now we can take a look. This is kind of the basics in this. In a castle or in a large building, you want to do this in several areas of your building, and between different buildings, you want to take different samples so you get an idea. Now, over time, when this crumbles, like in that picture we're seeing here again, where this has come off, that is usually from environmental impacts caused by rain, water, because of a lack of roof. It also can be caused under certain circumstances when the brick is cold and there is a draft going through that room or along that wall with moist, humid air. That is usually the scenario you have in the basement. That means you have an air leak somewhere in the ceiling area, and the moist air comes from the outside through the door underneath the door sill into the basement room, and then it usually it's drawn to the cold. Warm air is drawn always into the cold. A wall which is basically directly connected to the earth ground behind it, say like when you build a house in the hill, even with insulation and concrete on the outside, will cool down to the temperature of the ground, which can be in altitude around 5 to 10 degrees Celsius. So if you have 30, 35 or 40 degree warm air with a 70% humidity or higher, that air will go straight to the wall, and then it will travel up the wall to wherever it can find the exit. And this is what we got here, most likely at Maya's place in one of her basements. That is a twofold issue of what this looks like it. For one is we can see that she put these support braces in there for the two beams, the floor joists from above. And we can see that one is kind of on the right-hand corner. We can see that there is some damage to it, and it looks like that is water-related as well. Water from the outside, say like if your roof is leaking, or if you don't have a gutter system on your roof, will eventually travel down any wall, and then will find its way into the building because water travels only the path of least resistance. Eventually, it will find the grout, and it will go through the grout all the way back into the ground or into the floor basement and then go out, and then you wind up with the green mold. Green mold in general is not a very dangerous substance, but it can be dangerous for a certain group of people. That is primarily people with respiratory illnesses like asthma or people who had COVID, you know, in a very bad way, where they were hospitalized and we went on ventilators and stuff like this. And it is an extreme irritant to your eyes and to your sinuses primarily. It can cause rash or even an itching and that sort of stuff. So with mold in general, this is something you have to be very careful. And that brings me now to the next thing, is I use for mold removal another caustic solution, which we usually is known as caustic soda, the more aggressive version of baking soda. They're not exactly the same, but roughly. It's both a soda. The caustic soda, the way you deal with this is you get caustic soda or sodium dioxide, what it is called by its trade name. You buy a 250 grams, 500 grams, half a kilogram, that should be fine. And you use distilled water and you need a pH tester. What you do is you mix, that's very important. You always have to put the acid or the caustic base into the water. Never mix water to any of these things, either acidic or caustic, because the water will immediately react with those substances and it will fume and can explode and can do all sorts of stuff. That's a serious way to get injured, and especially with caustic soda. So make sure you add the caustic soda to the distilled water, and they come in these little pebbles, and you take one at a time. You dissolve this completely. You do a pH test. You want to come ideally to a pH level of about 10 to 10.9. You need to use a face shield, rubber gloves, clothing, which, you know, lab coats and that sort of stuff, which are made out of synthetic material. You do not want to use anything where it's made out of cotton, because that stuff will eat cotton up in a split second. It also will burn on your skin, and you're sure you don't want to get that in your eyes. And you probably, the best thing is to use a apron and rubber boots, a rubber apron and rubber boots, like a regular lab outfit you would use for that, and a breathing mask. It doesn't have a very strong odor, but since it is caustic, when you inhale it, you're going to have a big cough coming up. I have experienced that before. And then you just spray that a little bit on there, on your mold, on your green mold. You're not trying to disturb this by touching it or pushing anything against it. You don't want to have the spores fly through the room. That's the last thing you want. You want to kill this stuff off as quickly as possible. And usually what happens, it depends on how big the growth is of that green mold or black mold, for instance. The caustic soda will probably kill this within a minute to 2 minutes. It should change its color. When it becomes a grayish white, then you know that this stuff is no longer alive. The fungi has died effectively. So the capillary effect, that caustic solution you've sprayed on the wall, you don't overspray it. You don't want it dripping down, just enough to cover that area which is infected by green mold. It will then soak into the brick and the wall, because it's the capillary effect, and it will travel along. And that will do two things. It is going to restore the pH level in your existing water back to what it should have been in the first place. That means under certain circumstances, if the sand is not too contaminated now in there after all these decades or hundreds of years or whatever it might be, it will actually reglue itself. So now you don't have to worry about it. It is not a real fix to glue or to re-support internal structures, especially on thick walls. You won't go very far, but it will stabilize the whole thing more than what it is. It will not be as easily coming off where you can just go over with your finger and the whole mortar just crumbles out of the crevices, out of the gaps. The other thing is, what you can't see is the growth of mold. And for that, what you want to do is you can go to an automotive supply store. They have little flashlights which have a UV light built in. The car mechanics use this to chase leaks in the air conditioning system in your car by putting a dye in there, greenish, yellowish dye. It looks very much like your green mold on the wall. And in complete darkness, when you turn that ultraviolet light on, you will see every spot where the fungus actually is, even when it is not visible to the naked eye. And then you can go again and spray a little bit in there. I use the old spray bottles, say like from Windex or 409. I wash them out and I put the stuff in there. I mix probably a quarter liter or less at the very most of this. And then the way you basically dispose of it is, since it is caustic, is you would have to find something acidic like vinegar. And you pour a little bit of vinegar in there until you reach a pH level 7. So it is normal, and then you can actually just dump it out in with the drain in, and it will just go into the natural system. There's no heavy metals, no pollution involved in this. It is just important that the pH level is 7 when it is disposed of in those quantities what we're looking at. So this is now on how you deal with this green mold. Now we're going to take a look at Nick. No, not at Nick. Dan is his name. That is that fellow who bought that castle, which we're seeing now here. And you can see it has no more roof. This was a little time ago. They're now much further into construction. And here we can see a steel beam, which is kind of bent out of shape. And that steel beam, they had a fire in there. I'm not exactly sure on what part the fire actually started or what floor. But it was in one of the rooms. The lady had left a cigarette there, I guess the owner, and it was probably the walk-in closet, and the clothes caught fire, and then the whole thing went up in smoke. And by the time the fire department got there, everything was basically up in flames, and it kind of burned down. And then whatever didn't burn down was then damaged by the rain coming in. And here we can see now the heat damage which the fire did to the steel beam by the way the steel beam has bent out and buckled, and that is typical. And this is exactly on how the World Trade Center in New York collapsed. When the airplanes hit the World Trade Center, the jet fuel they had on board ignited, and that was a massive amount of jet fuel they had because they had just taken off from very nearby airports. And that was such an intense heat that the steel beams, similar to the way you're seeing this in here, basically started to buckle and to shrink, and that collapsed the top floors, and then the whole thing came down. And this is pretty much the scenario you had here as well in that castle. This is what took place. That leaves us with a question of the integrity of the outside walls itself, which are these 3 corner sides. You know, you see there's 2 corners. Rooms which come up. To what an extent. This would take a static expert to determine this. Because the lime at that heat being reheated again to these temperatures, which can not necessarily melt but deform steel beams, is very intense. I would say probably you're looking at temperatures of around 1,000 degrees Celsius. And that will cause some damage to the entire mortar in the wall, and possibly have split bricks apart, which you can see they're probably cracked or they have hairline cracks. That is something which has to be investigated before you actually put a full load on the floor itself. Dan and his friends, they have started to put new steel beams in. They're building that up because some of these steel beams, they anchored already prior to the fire. They had also an anchor function into the wall to keep the wall from falling over. And here's what we can see now is in the other video I had explained that our castle in Kamieniec which is in Poland today, or Kamenz of German, that was the name of the town, had 6-foot walls, and then the walls would go thinner as the building went up. Kamieniec is similarly constructed. It is a 3.5-story building as well, but here the walls are much thicker. And construction steel came about 1860, 1870. This came out of this whole industrialization with the railroad and everything else what came with it, and the steel making processes, and the capability of bringing coal, high quality coal, which is usually anthracite coal versus brown coal, to the mills, steel mills basically, where they were able to produce that steel. It's a very dirty process where iron ore is basically converted in a steel mill to steel, to construction steel. 1886 is also around the time when the Brooklyn Bridge and the other bridges in and around Manhattan and other places in Europe were constructed. And it was also then the time when the Eiffel Tower was in Paris was constructed, because the steel became available and the ability to rivet, to drill into the steel and to rivet the steel beams together. So this is why we have here a single wall going basically from the basement foundation all the way up to the 3rd floor in just a brick width basically. Whatever that is, like I said, is about a foot or less than a foot, probably 20 inches. Might be only about 15 centimeters, could be 20 centimeters, somewhere in that range. So that wall is a lot thinner than what we have, for instance, at the castle in Kamieniec, which would have had 6-foot walls in the basement, 4-foot wall on the 1st floor, 3 foot on the 2nd floor, and 1 foot on the 3rd floor, basically. That is roughly on how this is staggered up, so it gives you that shape to transfer the weight down into the full. That was done without any construction steel, because with wood joists, lumber joists, you cannot do this. You're not going to get the physical strength out of this over the spans. They're probably 4 meter, 5 meter, 6 meter spans they got in there. And that wouldn't work very well. So they used already construction steel. And it was pretty much a state-of-the-art building when they started to build that particular castle in 1886 by employing this. But that proved later, now, a more bigger challenge after the fire because of the possible damage and the loss of the inherent static stability of the walls. And the walls which are mostly affected by this are the ones where most of the fire actually happened. So those are the ones which have to be definitely investigated. That was something I wanted to mention in here because, like I said, so a fire can affect, now we know this, can affect the pH level and the composition, or the, gluing capability, so to speak, the adhesion properties of a lime and sand, which we know normally at mortar. Mortar at this time, just for your information, was about 1 part of lime to 2.5 parts of sand. For plaster, you would go up to 3 to 4 parts of sand with a very fine sand. And you want to get a very light colored sand, so you have a white plaster then. Just to give you an idea, stucco, on the other hand, is for the outside. That is usually more aggressive. That is larger sand, but also with lime in it. Today we use more of a concrete base for this that gives it a more sturdy and longer lasting consistency, or longer lasting quality in this. Now we're going to come to the acid rain. Now you wonder, why acid rain? Well, I started to explain that at about 1840 the railroad came about, which gave us the steel, we needed, and that made it possible, the Industrial Revolution. And as soon as the railroad and steamships on rivers, primarily took off, the immediate impacts of coal burning was felt all along, either along the railroad line or along the ship line on the river. And that was the way that manifested itself. It was almost as soon as the first steam locomotive came into town, all of the housewives, at that point it was all housewives, were up in arms because they had laundry lines outside behind the houses usually, where they would hang up their clothing and their linens, their bed linens and all of that stuff, usually white, to dry for after washing. And when you had the steam engines, the steam locomotives come by, and they started up when they left the train station, that sent a huge cloud of black smoke in the air. And that black smoke had unburned coal particles in there, since they use coal, since it has more firing capabilities. And that settled on the white, freshly washed linens. So that was the first experience humanity had with the Industrial Revolution and pollution to begin with. One thing they didn't know about in 1840, when this really started to take off and it got basically progressively worse, was the interaction of the exhaust fumes from burning coal, especially at high temperatures, and brown coal here particularly, on how this interacted with the cloud system. This was before anyone thought about global warming, because there was a prior stage. Now, we also have to notice that this whole thing basically fed each other. The coal, which was the most desirable one, which has the highest burning rate, the highest kilojoule, basically, so to speak, in terms of firing power, is anthracite coal. And for instance, in Germany, anthracite coal was primarily found in two areas. That is between Cologne and Düsseldorf, in Bonn, or along the Rhine on the left Rhine bank when you go towards Holland, and then in Upper Silesia, in Opeln primarily. This is mined, so you have to go underground, bring it up, and then you have to transport it. Until the railroad came along, the most powerful transport mechanism for everyday use was an ox cart. I found only a miniature scale model of what they looked like, and that is what you're looking at right now. The only pictures I found on Google is the two-wheel version, which is half the size of this thing. The ox cart was able to carry 7 metric tons at approximately 2 miles per hour. So you can understand now on how difficult it was prior to the railroad coming into town, and how to move heavy building material, lumber, or anything of that nature. The ox carts stayed in existence until basically trucks came about 1910, 1920. And they would transport now the local lumber and the local burnt lime in blocks, 7 tons at a time, to the local train station, where then was unloaded and loaded into a regular cargo container, the old boxcars they used to have, and then they transported it around, and they had open lorries for the coal. So now you could transport coal anywhere where there was a railroad, and then from there it could be distributed down for local delivery on an ox cart. That's basically on how this worked. But the great advantage was the railroad was able to use anthracite coal, and brown coal was only used in homes. That was the cheap alternative. It can be mined by just removing the topsoil, and then you start basically just cutting it down. And you're getting it. But it burns. It has a much higher sulfur dioxide content, by far higher than anthracite coal. And so this is how this all developed. So they had pollution. The pollution was black flakes basically flying everywhere, wherever there was steam involved, steam engines. And that sulfur dioxide will react with clouds when they form their water droplets when it starts raining, and it becomes a sulfuric acid basically. This phenomenon took off after 1945, when Germany was divided between East and West Germany. East Germany doesn't have, or had very limited anthracite coal, but they had massive amounts of brown coal. So they started to dig up all of this brown coal they had, and they built one brown coal power plant after another to produce electricity to fuel their reindustrialization again in the 1950s and 60s. So that Poland and many other countries, Poland had more anthracite coal, other countries had more brown coal. Some countries like Romania and Bulgaria didn't build that many coal power plants to begin with. And in West Germany, we had the coal power plants fueled by the anthracite coal. But by 1980, and this is what you're seeing here, 1981 in November, the Spiegel magazine published a front page report from a scientist who said that the coal burning was basically causing caustic rain. And what this did is the caustic rain would come down in the highest concentration in the higher elevations like the Black Forest and the Austrian regions in Switzerland and in Poland and in Silesia. And it would basically feed the rain would go into the ground, and especially the fir trees and the pine trees. I think those were the two types which were mostly affected because they're flat rooters, or I don't know what you call it. They have the one that goes down and the other ones they spread out. They're the ones who spread out. They absorbed most of this, and that caused the needles to turn brown and eventually fall off, and the trees looked like this in this picture here. And what they then came up with by 1982, Helmut Kohl was our chancellor at that point, and he jumped on it. And they mandated that all the German coal power plants had to have scrubbers. And the legislation was enacted that any type of vehicle built after 1991, I think, had to have a catalytic converter built in and run on unleaded gasoline, because that also caused quite some environmental damage. And with the caustic rain, they came up with the idea to drop lime, the same basically what you're using there, onto the grounds of the forest. So they would fly up with a helicopter and they would drop massive amounts of lime all over Germany, West Germany in the forests. That neutralized the acidious rain because you have now a caustic base on the ground, and that came then close to a pH level of 7, and that neutralized it, and that basically then the trees were able to be reforested, so to speak, and they regrew, and it was no longer a problem. The main culprit, however, in this was, and this is why they did this with the lime helicopter, so to speak, was until East Germany collapsed and Germany reunified. As soon as Germany was reunified, all of the coal power plants were switched over to West German anthracite coal, and they put scrubbers in there. That was the first thing. They shut down everything that had to do with brown coal. Everything came to a stop immediately. When Helmut Kohl went over in 1990 for the election to be elected by the East German people as a common chancellor, basically, he said he's gonna promise them flowering or blossoming nature countryside, because everything was dead over there from that overuse of the brown coal. All of this brown coal stuff, that fallout from East Germany, traveled to France, traveled as far as Portugal and Spain, went into Poland, the Ukraine, the Baltic states, Romania, Hungary. Almost every country was affected by it because they put out so much. This acid is the cause of why you're looking at this brick with the outer layer missing, because that fire happened in 1986 and the coal firing of these plants didn't stop until 1991. So that particular wall was exposed to the acid rain for almost 4 or 5 years, and this is the damage you're seeing. And this is most likely the reason why you're seeing this, because the acid will react from the acid rain, from the sulfuric acid, basically in a probably pH 6 or so, maybe 5, if it gets really bad, will break down and react with the caustic pH level left over in the lime. That neutralizes it. And that's why we're doing the tests with the pH tester. So I hope all of this made sense to you. And the way you can fix this really only is by scraping as much of the destroyed lime out, which has a neutral pH level, and putting, if possible, the same amount or the same type, grade sand, grain sand with about the same mixture, which is most likely going to be 2 to 2.5, 1 part of lime to 2.5 parts of sand, into these openings, basically, into the slots, cavities, whatever you want to call them. And basically reseal the entire wall. It doesn't matter if that is stone or if it is brick. When you have this stuff crumbling out, you're going to be sitting there, pretty much so, and filling up all of the old joints, basically, redoing the joints. On a regular house, it might be a project for 3-4 weeks when you have 2 people helping you. On a large castle, that can take quite some time, but it is the most important thing in the restoration. And if you have any pH, higher pH than 7 left on the center of your wall, then you're going to be really in a good shape, because now the new mortar on the outside with the correct pH level of 10 to 10.9 will prevent any further deterioration of the internal mortar, which is still the original one. So that's kind of how this works. If static questions are involved, then I would strongly suggest that you consult a static expert, an architect who is familiar with this. My experience with this is the most experienced people with this kind of stuff are the ones which are involved in the upkeep and restoration of cathedrals. So if you're in France, for instance, I would call the rectory of your next bigger town, where they usually have a large-scale cathedral, the church rectory, and ask them if they can tell you who their expert is for the mortar and the brickwork and that stuff, the stone mason stuff. They will probably tell you that, and I would call these people and ask them if they could come out to my building, whatever it is. On a castle, it's probably more justified, or on a chateau, than it is with a barn, where you can just glue it together however it's going to hold, since you have only one level. But on a multi-story building, I would definitely call these people up and have them come out and further examine this to get a full expert analysis of the structural soundness of the building. And with that, you have a great evening.